Before we learn about the second derivative test, we have to talk about concavity. And you've seen concavity perhaps in science class, with lenses, being concave and convex. We're just going to worry about concave only in calculus. You can either be concave up or concave down. Concave up looks like this. Like a parabola that opens upward. That's concave up. In fact, if I put a P right there, it almost looks like the word up. And concave down looks like this. In fact, D-O-W-N. Look at that. Concave down. Down like a frown. Oh, so sad. So that's kind of how I remember it. You can also be increasing or decreasing. And so I want to talk about these 4 different scenarios. These are the only 4 that we have. I'll start with the first one. The first graph is increasing. You can see that it's increasing. You can see that it's rising. But not only is it rising, it's also smiling. It almost looks like, if I put a little eyes and nose, it looks like this part of this person's mouth right over here going like that. It's concave up. The slope is getting increasingly larger as you head from left to right. The next one, it's also rising, but it's not happy. In fact, I can see some red here for me. That's concave down like a frown. It's part of this person's frown, if you will, the left side of their face. I think the best way to kind of explain these 4 cases is to use some sports analogies. Don't worry, I'm not going to use sports analogies all year long. My biology teacher in high school was the head football coach as well, and every analogy he ever made was football related, and the girls couldn't stand it. It was crazy. But I think it's going to bode well here. Look at this first one. We're going to say that increasing is winning. So this team is winning, but they're also smiling. They're also happy. They get along. The locker room's a fun place to be. If it was the NFL, it would be the Kansas City Chiefs right now. They just won the Super Bowl. Patrick Mahomes is amazing. Wow. Or in years past, it's been the New England Patriots for a while, too. You could be increasing, however, but the team doesn't get along. Maybe you've played on some teams like that where, maybe the high school soccer team somewhere is winning games 1-0, but the guy that scored the goal or the girl that scored the goal, went 1-on-3 with a whole host of defenders, and you were wide open in front of the goal. They could have slid a pass right over to you for a wide open tap in, but instead they decided to shoot a really difficult shot. It went in anyway, and the team won, and they were in the newspaper, and woo, but not everybody's happy. There's some infighting going on. You almost got the sense if this season went on any longer, you might start to turn the corner and start losing. So, yeah, you're winning, yeah, you're rising, you're increasing, but you're concave down like a frown. Conversely, let's continue with the soccer motif. I was the head coach of my daughter's U8 team. I think I was volunteered as the coach because I was a teacher, and basically everybody else stepped backwards, and there I was. It's like either I coach or the team doesn't play. And we were in a travel league because we only had 2 teams in town, and we were god-awful. I mean, the kids had no idea. They're all 7.5-year-old girls. They didn't know what they're doing. And I was like, you're on defense. You're a defender. And they would go stand in front of the wrong end. And we're like, oh, it was so bad. And we went to Broadview Heights, and they beat us 8-0. But truth be told, they could have named their score. It was 5-0 before anybody even realized the game had started. Their coach calls timeout, pulls the team into a huddle, and I'm thinking, dude, really? And I heard him whisper, don't shoot at the goal. They still beat us 8-0, but he was having them pass it around, and they took it easy on us. We were terrible. We lost just about every game that we played in, and we got humbled. But as the season went along, you could see improvement. Don't get me wrong, we were still losing, but instead of losing 8-0, we were losing 3-1, 5-2. We were still terrible, but not as terrible as before. And you could see smiles on the parents' faces. They realized we were getting better. if the season had gone on another 100 games, maybe we'd start winning. We actually tied our last game 2-2, so I mean, we're getting a draw and stuff. So, but yeah, we were awful, but we were happy. We had the orange slices at halftime. Yeah, it was fun. I told the girls if they scored in the last game, it was all muddy, I'd slide in the mud, and we actually scored twice. Oh. So I was like covered head to toe in mud. My wife was kind of mad, but it was cool. And then finally, you could be on a team that's losing and everybody just hates each other. Nordonia basketball comes to mind. My junior year when we went 2-19, that season could not have ended any sooner. It just sucked. Thank God Ravenna was in our conference when we played them twice because they were winless. Those were our 2 wins. So anyway, we were falling and frowning. So we were decreasing and concave down. So hopefully that helps give a visual to this. Now for some more mathematical inferences. F double prime of x, of course, is the way to say the second derivative. If the second derivative is positive, it means that you're concave up. Okay, so you're going to look like this. If the second derivative is negative, you're going to be concave down like this, down like a frown. You have this thing called a point of inflection. And a point of inflection is simply where the concavity changes. Let me just show you an example of a point of inflection in a graph. Let's say you have this graph that kind of looks like this cool S-curve here. The point of inflection on this graph is right here where this little star is. And the reason why is because you started out concave down like a frown. And then suddenly you hit the point of inflection and you became concave up like part of a smile. The concavity changed right here, so that's called a point of inflection, or POI for short. Okay, you can also go from concave, up to concave down at a point of inflection. A point of inflection happens when the second derivative, f double prime of c, is either 0 or undefined. Undefined is kind of harder to show, but you can have a point of inflection. Here's one. You start out concave down like a frown. You end up being concave up like a smile. But right there, that's a nasty cusp. There is no first derivative there, so therefore there can't be a second derivative either. So once in a while, you can get a point of inflection at a place where the second derivative is undefined. Normally, the second derivative is 0. The key is that the second derivative has to change signs. You can't go from positive to positive and claim that the concavity changed. It didn't. Okay? Finally, last but not least, and most importantly, as a matter of fact, is this thing that I put 2 stars by. Just because the second derivative is 0 doesn't guarantee that you've got a point of inflection somewhere. Let me show you a counterexample of this. I'll start with y equals x to the 4th. If you were to graph that, here's what it would look like. Make my x and y axis here. Y equals x to the 4th kind of looks like a parabola, except it has kind of a wide butt. That's really what it is. It can't go negative, because even if you put negative numbers into the equation, you're taking it to the 4th power, so it will look like a U shape. Let's take a couple derivatives of it. Y prime, derivative there, using the shortcut power rule, is 4x to the 3rd. Y double prime, I'll try to squeeze this in here, is 12x squared. Okay, let's say you took the second derivative, the 12x squared, and you're like, I'm going to set that bad boy equal to 0. Then what would happen is x would become 0. And then people were like, hey, x is 0. It's a point of inflection. I'm like, That's a min. There's no point of inflection at all. That thing's been concave up its whole life. So just because the second derivative is 0 doesn't mean you have to be a point of inflection. But the converse is true. If you are a point of inflection, then your second derivative had to be 0, or once in a while undefined. If that was confusing, you have to understand it eventually, because that is a way that College Board will try to trick you on a multiple choice question at least once, sometimes more than once, in the AP exam in May. They'll try to get you to think that the second derivative being 0 forces a point of inflection. I guarantee it's coming your way. So if you're still confused, here's a different analogy I use sometimes. Let's take myself. Let's say I was running for President of the United States, which I have no desire to ever do that job. But let's just say I did. People are like, Jeff, I think you should be president. You do a better job than the last 4 people we've had. I'm like, I don't know, maybe. Okay. Well, am I qualified? Well, sadly, there's really only 2 qualifications, and I meet them both. That shows you how low the bar is. I'm a natural-born U.S. citizen. I've lived here all my life. I was born in Garfield Heights, Ohio, so, good old Marymount Hospital. So I've checked off that box, and I'm at least 35 years old. In fact, I'm well above that. So I could theoretically run for president. Just because I'm eligible doesn't mean I need to take the gig. And it's the same thing here. To be president, you have to, have those things. You have to be naturally born. You have to live in the country for a certain amount of time. I don't remember how long it is. I've lived here all my life. And you have to be at least 35. To be a point of inflection, it's the same thing. You have to make the derivative equal to 0. I get it. It's eligible. Just like I'm eligible to be president doesn't mean I have to be president. Just because the second derivative is 0 and it checks off that box doesn't guarantee that it has to accept the position. It doesn't have to be point of inflection. It just means it's eligible. And here's a classic counterexample of it right here. So hopefully that helped. I'm sorry I babbled so long. Let's do some example problems. That's really the best way to learn is to practice. Numero uno. It says find the points of inflection, then determine the intervals where the function is either concave up or concave down. So first things first, a point of inflection means I need to take 2 derivatives. So I'll do this first derivative in red. That's going to be 6x to the 5th minus 30x to the 4th plus, 7.5 times 4. That's going to be 30 again, x to the 3rd. And of course, the derivative of 1 is 0. Okay, that's first derivative. I don't need the first derivative except to get to the second derivative. The second derivative, also known as f double prime of x, would be 30x to the 4th minus 120x to the 3rd plus 90x squared. Okay, I want to find the points of inflection, so I need to make that second derivative equal to 0 or undefined. Well, there's no way to make it undefined. If there had been a fraction or a square root, there are places where it can go undefined, but in this case, setting it equal to 0 is good enough. Now, like I just got done saying on the last slide, just because the second derivative is equal to 0 is not enough evidence to prove that it's a point of inflection. I've got to do a little bit more than just that. But for now, it's a good starting point. So I'm going to work my algebra 1. I'll start out by factoring. I can take out a 30x squared, leaving me with x squared minus 4x plus 3. Okay, still equal to 0. That also factors into x minus 1, x minus 3. And just so the 30x squared doesn't feel left out, I'll give it its own parentheses. Okay, so there are 3 places where points of inflection could occur. X equals 0, 1, or 3. There cannot be a point of inflection at x equals 4, because 4 would have had to show its face. So there's only 3 places that are eligible to be points of inflection. That doesn't mean they're going to accept the position. They don't have to take the job. So what I have to do now, kind of like I did earlier in the beginning of the chapter, is I'm going to make a sign chart, but this time instead of rising and falling, it's going to be like concave up and concave down. So here I go. Okay, let's try a number less than 0, something negative. Again, I'm plugging it in to the second derivative, which is right here. You know, that 30x squared in the beginning, it doesn't matter what I plug in. That's going to be positive no matter what. Unless I plug in a 0, but I can't plug in a 0, it's a border point. So that's positive all the time. Let me keep score right here. This is always positive. All right, let's plug a negative number into here. Let's say I'll plug in, I don't know, -5. Well, that's going to be negative. This will also be negative. Positive times negative is positive. If the second derivative is positive, I'm concave up. Okay, cool. Let's try a number between 0 and 1. How about 1/2? Again, the first parentheses is positive all the time. I'm just going to make that red. That's never going to change. If I plug in a 1/2 to the two parentheses here, they're still both negatives. So it's still going to be positive times negative times negative. It's still going to be concave up. So what that means is the concavity did not change at 0. So 0 is not a point of inflection. And I can see it already, even though it's months away. College Board's going to be find all the points of inflection, and a couple of the choices will have 0 in it, and people are going to bite on it. Don't be fooled. You've got to make your sign chart. All right, trying a number between 1 and 3. Let's put a 2 in. Again, first parentheses is still positive. If you put a 2 in here, 2 minus 1 is positive now. But 2 minus 3 is still negative. And positive times negative is negative. That's concave down if the second derivative is negative. Aha! There's a point of inflection at 1 because the concavity changed from concave up to concave down. Finally, putting in a number larger than 3, let's say we put in a 10 or something like that, all 3 of these parentheses are going to end up being positive, 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 positive. Once again, that's back to concave up again. And since you went from concave down to concave up, there's another point of inflection at x equals 3. Now, since it says points of inflection, not x-coordinates of inflection, points of inflection, you need to give me points. Don't just say x equals 1 and x equals 3. It's 1 comma something and 3 comma something. Unfortunately, you have to plug the 1 and the 3 into the original equation. It gets a little nasty, so obviously you're allowed to use your calculator for that. And just to save a little bit of time, I'll let you know what those answers were. Okay, and there we have it. The points of inflection are at 1 comma 3.5, or 7/2, and at 3 comma negative 120.5, or negative 241/2. Okay, so that's points of inflection. And then determine the intervals where the function's concave up or concave down. Well, thanks to the drawing that I made, we're already good. We know that it's concave down between 1 and 3, and it's concave up everywhere else. I just have to state that. And unlike rising and falling, unlike increasing and decreasing, it's not hard bracket. It's curly parentheses, the way that we kind of hoped it would be. So for points of inflection and concavity, it's just sort of back to normal. So let me write that down as well. There you have it. I've answered everything. Notice again, curly parentheses everywhere this time, not hard brackets. And notice I also didn't mention the 0 in my answer because 0 was not a point of discontinuity. It just showed up in the factoring, but it ended up not influencing the answer at all. So it is concave up the entire way right here between negative infinity and positive 1. All right, there's number 1. Onward. Okay, number 2, same instructions. Let's just go for it and see what happens. Let's get the first 2 derivatives. You can pause me if you want. I'll just throw them down right now. There's y prime and y double prime, which I'm going to set equal to 0. And again, y double prime, if I want points of inflection, either has to be equal to 0 or undefined. Again, we don't have to worry about this being undefined. It's just simply an upside-down parabola at that point. I can factor out a negative 3, leaving me with x squared plus 6x minus, 48 divided by 3 is 16. You've got to love it when your teacher comes up with a problem whose second derivative factors, not to brag or anything, but man, woohoo! That's awesome. That's going to be x plus 8, x minus 2. Okay, So there's only two locations that might be points of inflection. X would have to be either -8 or +2. I'm going to go ahead and just make my sign chart right now. Those will be the border points. Let's try something into the second derivative. If you try a -9, both parentheses here and here will be negative. And the first parentheses, that -3 is negative all the time. A lot of people, when they factor, they get sloppy and they don't write this -3 right here. And what happens is this doesn't appear and their entire answer is all backwards. Now, obviously, I don't take off full credit for that, but man, if you factor out a negative, you've got to write it. If you factor out a positive number, it's not as big a deal. I write it anyway, but if you factor out a negative, boy, you gotta write it down. Okay, so 3 negatives multiplied together makes a negative. If the second derivative is negative, I am concave down. Okay, let's try a number in between -8 and +2. I'll go for 0. If you plug a 0 in, here and here, this middle one will turn positive. The other two parentheses are still negatives. Negative times negative is positive, of course. If the second derivative is positive, we are concave up, like a smile, which means yes, -8 something will be a point of inflection. The concavity did change there. And now something larger than 2, how about 10? It's an easy number to put in there. That's going to turn all three of these positive. And negative times positive is back to negative. If the second derivative is negative, you're concave down like a frown. And sure enough, you do get another point of inflection, this time at x equals 2. Since we want points of inflection and not x-coordinates of inflection, which is not a real thing, you have to have the y-coordinates as well. So yes, you have to plug the -8 and the +2 into the original equation. Now, your test and quizzes are going to be part calculator, part not. If I want the y-coordinate, I've got to give you a calculator. Same thing with College Board. If I want to see if you can do second derivatives and things without calculators, it's easy. I'll just ask you for the x-coordinate only. So, the same thing with College Board. That's what they'll do. But I want points of inflection, so we want x's and y's both. Here they are. And obviously, I think you can see from the sign chart where the function's concave up and concave down. It's concave up in between -8 and 2, concave down on the ends. Let me just jot that down as well so I can get full credit. And that's number 2. Hey, look at this. We've got ourselves a product rule. How about that? Okay, so this 2x is going to be the u. The x minus 1 squared will be the v. U prime v plus u v prime. U, and then v prime is going to be 2 x minus 1 of the first, no additional chain rule. Okay, so that's the first derivative. Second derivative is going to have more chain rules. I don't know if we really want to do that. Let's go ahead and factor. Let's take out a 2 and an x minus 1. That's going to leave me with just an x minus 1 off of this. I don't need the parentheses anymore. This plus sign is going to come down. This got taken out already, but this 2x, other 2x is still here. So really, the first derivative is 2 quantity x minus 1, quantity 3x minus 1. I'm going to have to make this, again, the u, and this the v. You can think of u as being 2x minus 2 if that helps out. All right, second derivative, one more product rule. U prime v plus u v prime. That is going to give us 2 quantity 3x minus 1. That's the u prime v. Plus the 2x minus 1 times v prime, which is times 3. Okay, that's going to be 6x minus 2. You have to treat this 2 times 3 as a 6. Imagine that as a 6. The 6 goes in. So plus 6x minus 6. That's going to end up being 12x minus 8. So that's the second derivative, 12x minus 8. We set that equal to 0. And luckily for us, that means there's only one place that can possibly be a point of inflection, and that's going to be positive 8/12, otherwise known as x equals 2/3. Hey, by the way, that was pretty crazy. Maybe you don't want to do all those product and quotient rules. Maybe you would prefer just to FOIL this out. Since it's only a second power, that's okay. Anything larger, you don't want to do this. You don't want to do this if it's a 22nd, obviously. But x minus 1 squared is easy enough. It's x squared minus 2x plus 1. And then if you do some distributive property to that, the original problem started out as 2x cubed minus 4x squared plus 2x. And I think the time that it takes to do that is well worth it. Because now when you take your first derivative, it's 6x squared minus 8x plus 2. And when you take another derivative, there's your 12x minus 8. And of course, the 2 is gone. That was a lot faster. So anyway, regardless, we've got x equals 2/3. That's going to be the point that we need to use. So I'll go ahead and put that right here. 2/3. Just have to try a left and a right region. Let's pick a number from the left. How about 0? We're going to plug it into the second derivative, which is right here. Don't need that equals 0 anymore. If you plug a 0 in there, I think it's easy to see that 0 minus 8. 0 minus 8 is negative, so it's going to be concave down. If you plug in a number larger than 2/3, let's say you plug a 1 in, you're going to get 12 minus 8. That's positive. So yes, there was a point of inflection there, and the point of inflection will be 2/3, comma, 4/27. Sometimes we're going to make you find the 4/27 without a calculator, so don't be afraid of that. If you know that x is 2/3, that 2x will be 4/3. And then you have something squared, so I'm just going to write 2 fraction bars. If you put the 2/3 in, 2/3 minus 1 is negative 1/3. And since it's squared, we'll just write it twice. See, that's 4/27. That's not going to hurt you. So don't feel like if I strip your calculator away from you, it's the end of the world. Just go with what you know. And then again, for the concavity, concave up and down, I think it's pretty obvious to see from the little sign chart that I made. Let me just write my answers. There you go. On number 3, I made a problem that looked like a product rule. There was kind of a way to get around that. There's no way to get around this. This is going to have to be a quotient rule, so you're going to have to just suck it up and do it. Even though the denominator factors into x plus 1, x minus 1, that's not going to help us at all. Although those are points of discontinuity, so we have to be aware of them. All right, let's see what happens. We got u prime v minus uv prime over v squared. Here's the v squared. That's the easy part for me. Okay, u prime v. Looks good. Minus u v prime. I'll do v prime first. V prime and then u. Okay. The good news is we're going to get some very nice canceling here. I have 2x to the third, but I can see that there's also going to be a minus 2x to the third. I won't write either one of those. We're just going to cancel anyway. And the negative 2x minus 10x, of course, that's just going to simplify to negative 12x. Okay, one more derivative. Again, we have to do quotient rule again. Good practice from last chapter. Or last year, perhaps, as the case may be. So u prime v minus uv prime over v squared. One more time. The denominator gets squared, so now it's x squared minus 1 quantity to the 4th power. Up top, we have u prime v, which would be negative 12 v minus u v prime. V prime is going to be 2 x squared minus 1 to the 1st power times a chain rule of 2x. So we've got some algebra to contend with. Let's simplify some things. I can take away an x squared minus 1 from all 3 terms. Remember, this is just one big term right here. And so is this. Okay, so that helps a little bit. I mean, I can also factor out a negative 12 in the numerator if I choose to. Let me simplify this second derivative up a little bit. It's looking pretty raggedy. I went ahead and distributed the first 2 to get the negative 12x squared plus 12. And then I combined this entire disaster to get the 48x squared. And I had a double negative right here. That's why I have the plus in front of it. In fact, I can combine some more like terms. 48x squared minus 12x squared is 36x squared. Let me just do that. Okay, so there's the second derivative. Now remember, defined points of inflection, the second derivative is either 0 or undefined. You can't set the second derivative equal to 0. There is no way to make the numerator 0. Those are both positive, no matter what you put in. So the only other thing to do is to look at the denominator and we can make the second derivative undefined, which does happen at 1 and at negative 1, which obviously weren't even in the original problem domain. So, we kind of knew that was coming. Let me go ahead and make a little sign chart once again. Okay, as I alluded to, this 3x squared plus 12 can't be negative or 0. It's going to be positive no matter what. So really, we're just concerned about what the denominator is. So if you try a number from the left-hand region, let's say we try negative 2 in there. Negative 2 squared, it would be 4. 4 minus 1, 3 to the 3rd, that's positive. So positive over positive is positive, concave up. Actually, the same thing happens if you go to the right-handed region and you try positive 2 in there, you're going to get the same thing. 4 minus 1 is, 3 to the 3rd. So that's also concave up. It's when you go into the middle and you try something like a 0 in here. 0 squared minus 1, that's negative 1 to the 3rd. That is negative. That is going to be concave down. And so you do have points of inflection at negative 1 and at positive 1. Or do you? What happens when you try to plug negative 1 and positive 1 into the original equation? You're dividing by 0. So those aren't points of inflection. But wait, the concavity changes. Yeah, but they don't have to be points of inflection. Concavity can change at vertical asymptotes, which is exactly what those are. So when it says find the points of inflection, there aren't any, which is really disconcerting after doing all that work. But the intervals where the function's concave up and concave down, I can still write that. So let me put my answer down. Again, notice that with concave up and concave down, they are curly parentheses, not hard brackets. Hard brackets are only for increasing and decreasing, if we were to ask about that. We'll finish up day 1 by doing number 5. This is a problem that I made up myself, but I patterned it after some FRQs that I've seen. It says a function f is continuous
on the closed interval -1 to 3. Notice it says continuous, not differentiable. And in fact, I see some DNEs there for the first and second derivatives, which means that we probably do have some corners and cusps, but it is continuous. This is a 4-part problem. We want to find all local extrema, maxes and mins. We just need the x coordinates, although honestly I could provide both if I wanted to. Part B, give me the intervals on which the function is concave up or concave down. Part C, we want the points of inflection, just the x coordinates. And then finally part D, sketch the graph that has all the given features. I'm going to go ahead and start with D first, going out of order. I think that'll make parts A, B, and C much easier because I'll have a picture to refer to. So here goes. All right, we know that the graph goes through 4 points. I can see that it goes through -2, -1, 0, 1, 1, -2, and 2, 0. So I'm just going to go ahead and plot those points right now. -2, -1, 0, 1, 1, -2, and 2, 0. Okay, so far so good. Let's take a look at the stretches in between those 2 points. In between -2 and 0, you can see that the first and second derivative are both positive, which means the graph is going to rise, but it's also going to be concave up, like a smile. So on this stretch of the graph, it's rising and concave up. Okay, so that takes care of that box right there, both of those. In between 0 and 1, both first and second derivative are negative, so it's falling and concave down, like a frown. It's going to look like that. And you can see that right up here at the point 0, 1, you've got yourself a cusp, and that makes sense because the derivative does not exist, so I'm actually happy to see that cusp. All right. Now, between +1 and +2, you can see that the first derivative is positive, so the graph is rising. But since the second derivative is 0, it's neither concave up nor concave down. It's just linear, straight line. So that satisfies that. And again, you get yourself another cusp at the point 1, -2, so the derivatives don't exist there. And again, that makes sense. So we've got ourselves a great-looking graph. Part D is done, and I can refer back to D when I do A, B, and C, which I'm going to try now. And I'll go in order. 5A says, find the x-coordinates of all the maxes and mins, the local extrema. All right, well, let's look at the graph. I can see that I have a max right here at 0, 1, and I have a min, a relative minimum, at the point 1, -2. All right. I should have been able to tell that anyway because you can see that the first derivative, which controls rising and falling, is changing signs at x equals 0. It's changing from positive to negative, which means the graph was rising, then falling. Positive slope to negative slope, so there should be a max there. And then similarly, at x equals 1, the first derivative is changing signs from negative to positive, so the slope was negative, then positive. That would indicate a min right there, which is exactly what we saw from the graph. So I simply have to put that in writing in a way that College Board would give me full credit on such a problem. So let me do that now. All right, there's a relative max at 0. And you cannot say the slope changes signs. College Board's going to want you to say f prime of x changes signs, or first derivative changes signs. And you have to say from positive to negative. It's not good enough just to say, it changes signs, because a min would change signs as well. Again, the reason that College Board wants to see f prime of x is there are students out there who have not made the connection that slope and first derivative are synonymous with each other. Personally, I think those students are in a world of hurt, but they want to make sure that you're not one of them. So we want to write it like that. Then here's the second part. Okay, 5B, we want to find the intervals with concavity. Here it doesn't say to explain, so we just need to state where it's concave up and concave down. And again, you can see it two different ways. You can see that it's certainly concave up right here. That's between -2 and 0. And it's concave down right here between 0 and 1. This portion of the graph does not have any concavity whatsoever. It's just a straight line. It's linear. Okay, you can also see from the chart that it's concave up between -2 and 0 because the second derivative is positive there. And the second derivative turns negative between 0 and 1, so it's concave down at that point. So we didn't need my picture from 5D to get those answers, but they are correct nonetheless. And finally, 5C wants the x-coordinates of any points of inflection. Well, there's only one point of inflection here. And from the graph, you can see right here up top that this max is also a point of inflection. Usually you don't get to be both, but here it is, because you're changing signs in the second derivative. We're going, in this case, from positive to negative. Now, this down here, this min, is not a point of inflection because you're not really changing signs. 0 is not considered to be a sign change from negative. So there is only one point of inflection. And again, the second derivative does not have to exist for there to be a point of inflection. Corners and cusps are certainly eligible. So we want to say there's a point of inflection at x equals 0 because f double prime of x changes signs there. And again, we don't want to say the concavity changes, even though that's true. College Board wants to make sure that we realize that concavity is linked to second derivative. You must mention the second derivative by name. Okay, so here goes. And that's it. Obviously, 5D is done already. And so we're done with day 1. I'll see you guys next time for day 2 of section 3C.